Right, Bismillahirrahmanirrahim. Welcome to the second lecture on Z transform. Right. So, what did we discuss last time? Firstly, we were switching domains, right? From what to what? Time to frequency. Yeah. And this part or this process of switching domain is transformation. So we call them transforms. Easy baat hai, right? Transformers, they switch from cars to robots and then back to cars, and they keep doing that all the time. That's the whole movie, right? So here hopefully we'll not just do that, we'll do something meaningful with those transformation, right? So what did we talk about in terms of the transformation? What was the key concept we discussed?
Three key concepts. First, I think
The sinusoids, complex
Hmm.
sinusoids,
Are the
sir,
eigenfunctions, right?
eigenfunctions.
So the key concept is actually eigenfunction and eigenvalue, and then we expanded on that, right? So we started with linear algebra ideas. We talked about eigenvalues, special eigenfunctions or eigenvectors being special vectors that go through the matrix unchanged. So I'm recapping this because, as I said, if you grasp all of this in Z transform, right, this lecture and maybe the next one after this, all three lectures together, uh, you are good to go with Fourier, Laplace, everything. It's just repetition then. Okay, so I'm just gonna repeat a few things. You may feel okay, I've heard this before, but I want to hammer it in really well. So the thing started with, we know there are vectors that are characteristics of different matrices. And this operation, we can always see it as a system. The A here is some system, right, through which x is going to pass, and what comes out, if it is x again with some scaling, right, we say x is our eigenvector, and the scaling it gets is the eigenvalue. Now this will not hold true for any other vector y. If y is not an eigenvector of A, you will not have some lambda, let's say this is lambda 1, lambda 2 y. You will not have that. If you have it, then y is also an eigenvector of A, right? So in general, this will not hold. So for that, we took the next logical step and we said, okay, what if we can write y as a linear combination of the eigenvectors of A? And that's where the idea of basis and spanning, all that comes. Yeah. So this is, we said, okay, let's make it A x1. Depending on the size of the matrix and everything, you can have more terms here, right? And the size of the vectors will also be different. But let's say for simplicity, we can form y as a linear combination of these two. Now if x1 and x2 do not span all this domain, then of course you will not be able to form all y's. But that's the idea. Bases have to span a given space, right? So um, once we had done this, we had an answer to this problem now, right? Which was that what is the output now? It is A lambda 1 x1 plus B lambda 2 x2, right? So what we did was, we got the basis functions, which were the eigenvectors of the matrix. We wrote general vector in terms of the basis functions, right? So we found the weights as you have to find, and then simply we passed it through and we found that you get the same vectors out, but what's happening, what's multiplying here, right? What is the multiplication? It's the yes, eigenvalue is here, that is contributed by going through A, right? But this is contributed by writing, yes, from the linear, so these are the linear combination weights, they are not eigenvalues. Eigenvalues come only when you pass y through A, then the system will add a multiplier here, but that's it. Otherwise x1, x2 are locked. Yeah. So this thing we said, okay, this you have done in matrices. We discussed that in detail. We said actually this thing can be generalized to systems. Yeah. And for now we looked at our subclass of systems, which was LTI system. So from here on we started saying, okay, now we're not just talking about any AX, right? We are talking about any general LTI system. And typically then what you write is S is operating on vector X, or we just write it like XT. You have seen it, right? It's just a notation. It's very similar to what there is before. But for LTI, let's just write LTI here. We said, okay, you know what made our job easier? In matrices, there is no general way. There is no general conclusion or say result or one general set of eigenvectors. Each matrix will have its own eigenvectors. There can be some classes of matrices that have similar eigenvectors, but usually you had to calculate them. Yeah. What makes our job easier here in LTI is this, that the whole class of LTI systems, yes, has complex sinusoids as its eigenvectors, or now we call them eigenfunctions, right? So complex sinusoid goes in, complex sinusoid comes out, okay, with some complex scaling. Okay, we've already used A, so I'll just use alpha maybe. Yeah, this can affect the amplitude of the sinusoid and the phase, but the overall shape of the sinusoid is the same. Yeah. So in this case now you don't have to find the eigen functions again and again. That step is now completely skipped. Why? We already know now LTI system. Actually, it's not just this. Today I will tell you there is a more general form, the complex exponential, which is basically Zn, where Z is any complex number. Any complex exponential. If n goes to infinity, we call it everlasting exponential. You have studied this as gamma n when we discuss it. So now we just replace it with Z, and Z is basically any complex number. You know the general form of a complex number, polar notation, if you remember. This was the amplitude, this was the angle, right? The distance from the origin and at what angle, if you remember the polar notation. So now Z is simply this, and Zn is the, I will come to that. So not just a complex exponential, this is a special case, sinusoid, this is a special case of the complex exponential. In fact, a Zn, if it goes in, what comes out is also Zn, okay, with some scaling. That is the general case. If in Zn you set alpha to 1, right, and phi to the frequency omega, you have what we call the complex sinusoid. So coming back to summarizing what we covered last time, you have LTI systems, you already have the eigenfunctions, you don't need to derive them again and again. So what can you do then? Well, if you can then write signals or your inputs in terms of these eigenfunctions, yeah, so that will lead you to a simple calculation here. So let's see that. What I want to also emphasize here is this. Let's say for real case, if a sine wave goes in, what will come out? It will be a sine wave of the same frequency.
Yeah.
Amplitude may have varied,
Yeah.
phase may have shifted. Okay, otherwise
Same.
same. Right. This is not true in general. Let's say there is an LTI system and a square wave goes in. Yeah, it will most likely, depending on what it is, it will change. It could turn into a triangular shape, it could be irregular. A lot of things can happen even within LTI. Okay, this result does not hold for everything else. For complex exponential or real exponential like this, exponential goes in, exponential comes out. Okay, the total amplitudes may have changed, it may have shifted, but it has the same shape. Okay, and this is in general. Actually, for the exponential case, we need to maybe draw it like this. Okay, with some sinusoidal frequency there. So, using these results, we are able to say, okay, now as an analogy to what we did over there, if I want to find the output of an LTI system to a particular input xn, right? What is the output? Previously we had done it as convolution, right? That was the equivalent of doing matrix multiplication or something. Yeah. Now using this technique, we don't go into finding the solution. First we find how can I rewrite xn as a linear combination of the eigen vectors. So for that I need to find these weights, right? And for that we have the Z transform. The Z transform, if we write it, is basically xz. The Z transform of a discrete time function signal xn is xn z minus n. Okay, and we will today define it more formally. For now, what I am telling you, these xz are now giving you these weights. When you solve it, the sequence you get will have these weights a, b, c. Okay, we don't need the functions, we already have them. If zn is an eigenfunction, so is z minus n. That's not a problem. But this thing we will call the Z transform. It will give you the weights. Now, if you send in, let's say, you have rewritten xn as a linear combination of these z's, or you have just taken the weights xz, what should come out? Yeah, then it's yz, the weights, the product of the weights will be xz, like you had here, a, right, this thing, b, those weights are here, but then where do the eigenvalues come from? Okay, today I will show you that those eigenvalues are actually the Z transform of Hn. So the system contributes eigenvalues through the impulse responses Z transform, and we will also see it has a special name. Just like this guy had a name, impulse response, this thing we call the transfer function. Transfer function. Why transfer function? Notice when you pass xz through this thing, that is when the system puts its multiplier. Like lambdas were put into the solution when this passed here, right?
Yeah.
So these are going to tell you how the weights are adjusted. Transfer function. Transferring from input to output. Yeah. So this will be a so today we will actually, last time I didn't really prove this, right? That eigenvalues here are actually the Z transform of the impulse response. How do I get this result? We will see that today also. Okay. How does this convolution turn into a multiplication? At least mathematically in this case, which we will write as Hz. Okay. And lastly, as I mentioned before, briefly I mentioned it last time also, when you do this in the transform domain, you are only working with the weights. Okay, You don't have the true output yet, which will be yn. This is just showing you the weights. It's only giving you this and this. You still need these to get the true yn, and that's where the inverse Z transform will come in. So we will also look at the inverse Z transform today. So basically, another way of saying it is that inverse Z transform takes you back from frequency domain to time domain. Okay, and the Z transform takes you from time domain to frequency domain. But really, you should always see it as what's happening. Z transform is giving you the weights you need to form. That's one thing. Inverse Z transform is telling you, I have the weights, because you use when we will write the formula. When you do the inverse Z transform, you need xz. So you say, I have the weights. Now tell me, how will this signal look like in time? Yn. Yes. So we don't need AVG. Right. So today, basically, this is more like summarizing what we did last time, but then also showing you what we will be discussing in detail today. Today we will try to make our discussion more formal, yeah, by bringing in definitions. And when definitions come in, things become a bit that's a bit more involved. There are some extra things that we have to consider. So for example, if somebody writes 1 by x, and if we want to go into detail, then we always have to write that x is not equal to 0, right? This is going into the depth, right? Making it more formal. Formal mathematics requires a lot of this kind of details, which maybe you want to skip, but to any mathematician, they don't like writing 1 by x. They get shivers. What if x is 0? Well, they don't want to imagine anything else. They want to imagine x equal to 0. Right? So when you write things formally, you have to add mathematical details that ensure that all people get same results. Right? Otherwise, 1 by 0 and n, which is nobody knows what that is. Yeah. So okay. So let's look at that now. Any questions so far? Not yet. If you can see this happening, this would also make sense. I know it might be a bit tricky for you to see that I'm talking about just the weights. What's really happening when we talk about weights is that when you take the Z transform here, it's equivalent to saying I'm not going to send in X, I'm going to send in A, B. Okay, that's what you're sending when you send the Z transform. And you get out when you get the output in Z domain, you are actually getting A, B times lambda 1, lambda 2. In fact, they are not added, so it has to be an element-wise product. So you will get A lambda 1, B lambda 2. Okay, this is what you are doing here. And when you take the inverse Z transform, you are saying, okay, now I have the weights. Give me what the output will actually look like in time. So the inverse, what it does, inverse says, okay, this weight was for the first eigenvector, this weight was for the second eigenvector, so I'll put them here. From this I will pick up the weights, I'll put them here, B lambda 2, and now you have yn. Yeah. So if you can grasp this whole thing, then you're mostly good with the key concept. Okay. So let's now come back to making this whole discussion more formal and proving some of the points. Yes. Firstly, as I have already mentioned, first thing, it's not just complex sinusoids that are eigenfunctions of LTI. It's their general version, which we will from now on write as Zn, where what is Z? Any complex number, right? Any complex number. Now, when I reviewed complex numbers with you in the second or third lecture of the course, if you remember, we mentioned that the general complex number can be written as Cartesian notation, or it can be written as alpha ej theta in the polar notation. So when I'm talking about z being any complex number, sometime I will say, okay, z is alpha ej theta. This is not restricting the number to any complex sinusoid or anything, right? It is just saying there is any complex number, because we know any complex number can be written in this notation. What makes it a complex exponential is this guy. Okay, exponential function पता है ना आपको, et जो होता है, जैसे continuous में क्या होता है, ये क्या है, grow कर रहा है, e minus t is decaying, that's the exponential. In complex case, you take a complex number and you raise it to power n. Now there is some additional detail that for this to be an eigenfunction of LTI, n has to be from minus infinity to infinity. Okay, they call it the everlasting exponential, which sounds very poetic, but it's a mathematical requirement. You don't have to worry too much about it. What we are saying is that if this we say is an eigenfunction of LTI, we mean that it goes on forever. If at any point you cut it, this thing is no longer an eigenfunction of the LTI. Not exactly, okay? But this, the requirement of infinity will not stop us. You have worked with sums of infinite series, right? You didn't say, okay, this is infinite series, I won't even try to sum it. You always do it, right? You find their limits, right? You try to apply different sandwich theorems to them to still find the solution. So here also, we will not let this extra detail restrict us or scare us away. So complex exponentials, everlasting complex exponentials, meaning n goes, I'm not going to write that, n goes minus infinity, just keep that in mind, where z is any complex number are eigenfunctions of LTI. Now, where do the sinusoids come in then? I've been talking about complex sinusoid. Well, that is a special case. This is your Zn, okay? And inside there, if you set alpha equals 1, okay? So alpha is the amplitude, and you make sure that theta is also, or it can be adjusted, but basically this has to be fixed, right? Then in this domain, this is the Ej. So just to emphasize, I could write theta n, but to emphasize a sinusoidal frequency, we usually write omega n. Okay, this is what we are talking about. So the complex exponential is inside here. As soon as we say that Zn is a eigenfunction of LTI, is the complex sinusoid is automatically an eigenfunction. So now we are saying Zn goes in, Zn comes out with some scaling, right? So of course this is a big claim. So first I should prove this, right? Let's do that. Yeah, a quick proof just to show you that this is not brought out of thin air. Maybe I should let you try it out first. What do you say? You want to try it quickly? Paper पे जरा try करें. So basically I'm saying xn is Zn. Time domain में है ना ये तो, right? Still xn is, the input is Zn. Now tell me what is yn, given that this is LTI and you're not going into frequency domain. Okay, to prove this, of course, the proof of this is going to set the foundation of frequency domain, so you cannot use that result already. Here you have to use your time domain results, right? So what do you know from time domain about the output? What do you need to know from me?
Impulse response.
Yes, good. So you have to ask me what is the impulse response. Let's say I tell you it's a general HN. Okay. Now show me that this assertion, if Zn goes in,
Yeah.
Zn comes out with some scaling, is true. So कैसे करेंगे? From what you know so far, leaving the frequency domain aside, which we are establishing now, what do you know about Yn? It's a convolution of Xn and Hn. So do that convolution and see what you get. Now you know Xn, it is Zn. You know Hn, some general Hn. We're not here to solve the whole thing to get some numbers. We're just here to prove a general principle that you should end up with a Yn that is some fixed multiplier and Zn. Right? This is you should end up with, starting with convolution. And convolution result we have already proven for LTI. Try कर हुआ कुछ नहीं कैमरा आप लोगों के अंदर मोड़ दो थोड़ी कौन जवाब निकला किसी से हुआ
I think summation के formula से ही होगा।
Summation के formulas यानी convolution, of course you have to use convolution. Okay, since you have given it some thought, hopefully you will receive this answer much better now. So let's see. We have already said that Yn will be convolution of Hn with Xn. Now how do we write convolution? First let's replace Xn by Zn, the everlasting complex, everlasting complex exponential. Yes? Why complex exponential? Remember, Z is a complex number. That's it. Okay. क्या था formula? Convolution का?
Summation
Summation something something. अभी तक याद नहीं हुआ? H k x n minus k यही था ना? एक को बस वो shift कर दें और move कर दें, right? यही था h k x n minus k. So let's write that here. Summation h k. What is x n minus k? If x n is z n, what is x n minus k? Z n minus k, right? So it's z n minus k. Agreed?
Yeah.
So far,
Yes.
nothing special here. Now notice, what is this summation over? That's important. What's this summation over in the convolution formula? Is it over n or k? It's over
And
k. Voting कराने right? It's over k. N तो आप यहाँ से देखते हैं. अगर भूल जाएं, just remember this. N is coming from here all the time, right? So it's the k that's in your control wrong. Yeah. So the summation is over k. That gives us an idea. This Zn minus k can be written as Zn times Z minus k. But Zn doesn't have to be in the summation, right? So it can be extracted, and that leaves you with hk z minus k. K is minus infinity to infinity, right? Over all k. Agreed?
Yeah.
But look at this. Notice we are already getting close to the form we wanted, yeah? Zn is here. Does this amount to a number? What does this remind you of? Which series? does it remind you of? Fibonacci. Sure.
Z
कुछ
transform.
तो कोई तो series है ना, और सही है.
Z
It's a
transform.
beautiful series, but yeah, that is the Z transform. But what series from before this, like calculus 1 and 2? Series कौन सी आती है आप? आप आगे जा. चलिए कोई basic series बताएं ना. Geometric series क्या होती है? A R N summation over n पे करते हैं, right? So over n, and then depending on the value of r, if it is less than 1 or greater than 1 in absolute, ये decaying होगी या फिर growing होगी. Convergent divergent वो सारा आपने देखा हुआ. अगर ये finite set है तो you can always find its value. In this case, we are not just looking at this, we are also changing the coefficients, right? That's fine. But in the end, it is a geometric series, a special kind of geometric series. ये देखिए, ये इसका exponent है जिसकी values minus infinity to infinity जा रही हैं. उनके जो weights हैं, जो यहाँ पे basic geometric series you always had fixed A. Now you have those weights changing as the impulse response weights, right? But now, what do we need for this answer to exist? This yn to exist, what do I need? Think like a mathematician now.
Need to be greater than 0.
Um, Greater than 0, okay. This is an infinite series, right? If this is divergent, if this series happens to be divergent, and since this series is not just a simple with A, so we cannot just judge based on R, we need to check the whole series. If this series is divergent, can you find yn?
No.
No. What's the condition for this answer to exist? It has to be convergent, right? So now this is where the assumption comes in, yeah? If this series is convergent, if it converges, yeah, we will call that result, whatever that result is, we will call that HZ. Okay. The Z transform of this thing, yeah? Z we can call it. Let's see if we have that here. Okay. So we gave it a name, yeah, this thing is, and we say that if this series is convergent, then the solution exists, which is what? Yn is now Hz times Zn, where Hz is a convergent series, so it should lead to some value times Zn, right? Now if this series is convergent, you have your answer. Did Zn go in and did Zn come out? Yes, under some condition. Now the interesting thing is that the only thing you need to do for this say series to be convergent is to see what values of Z are allowed. Okay, so I started by saying that any complex number is going to be allowed here, right? But now we are saying, okay, to really get this answer, you will have to only put values of Z here or use complex numbers that ensure that this series is convergent, okay? And this we will call the region of convergence. So this is, first we said you can take any complex number, so in the complex domain we said take anything. Now we are saying, okay, you can only take the values of Z, which will make sure that this series remains convergent. That might be within some unit circle, maybe it could be right half plane, left half plane, some irregular shape, anything. This thing we will call the radius of convergence. So whenever we define Z transform, we always also define its region of convergence. Okay. For the rest of our course, that region of convergence, except for finding it, does not have any special bearing on what we do. Okay, but it's good to know that. As I said, when we make things formal, we have to add details like x is not equal to. I shouldn't have to, right? Mostly, but we do. So same is here. Because if a mathematician looks at this and says, okay, I said Zn went in and Zn came out with, this is a summation, so it should lead to one value, right? I say, oh yeah, okay, Zn went in and Zn came out multiplied by one value. But a mathematician comes and said, no, but if this is divergent, what is that value? Oh, sorry, I don't know, right? So you can't leave it open. You have to bring in, okay, yeah, I see what your problem is. So what I'll say is, okay, Z has to be chosen so that this summation becomes convergent. And the allowed region of Z, that can be circular or whatever, we will call the region of convergence, right? So that is an additional thing. We will look at that. But what did we prove just now? What did we show just now? Our key assertion. What was our key assertion? That complex exponentials are eigenfunctions of LTI. We just showed it. Zn went in, you saw that, without anything else. We didn't know Hn, right? What did we know? Only one thing, that Hn comes from LTI. How did that help us? Knowing it, what did we use? We were able to use convolution. If I hadn't given you this, remember I've mentioned this many times, we proved it from the start. The whole idea of convolution is linked to LTI. If I hadn't given you this, you cannot do this, and then you cannot even get started. What do you do next? Yeah. So that's a separate course or set of courses what you should do. But for the broad class of LTI, only at knowing Hn, Zn goes through. And then there was this nuance, this extra detail, like x not equal to 0, this extra detail that Z cannot be chosen in a way that this thing becomes divergent, because then your assertion does not hold. Right. So that covers the key idea. Now, what's next? I have been mentioning, let's come to the second part. How was your lab, by the way? Sign in, sign out.
Yes,
right?
Yes,
So we didn't really do the transform, but that was linked to, I designed it so that you will see this thing, but we did that in real systems, right? With real data, because it's more easy to visualize. I hope you saw sine going in and sine out. And then we also showed you with sunspot cycle that even with two sinusoids you can start getting that shape. If you added more, actually you could get the exact shape. Okay, so that's where the Fourier, Z, Laplace come in, how to do that. But now I will, let's say, in movies and in some shows they show right half white, one half black, and things are happening in parallel or two different dimensions. वो जो आपकी है Stranger Things, कई दफा इकट्ठा दिखाते हैं, ऊपर ये हो रहा है नीचे ये हो रहा है, right? Yeah. So hopefully the transform domain is not that scary like the upside down, but still what we will try to now from now on write everything like that. There is upside, there is downside. Okay, none of them are scary, there are no monsters. Okay, neither of that. So upside is the time, sorry, xn goes in, system is LTI as is for the whole course, right? And there's an impulse response which is also in time. The output is a convolution of xn with hn. That's the upside, right? Now we are ready to go to the downside, and we'll prove the last part bit also today. Xz, if you don't work with the full signal, you just work with the weights, then you need the the eigenvalues are contributed by Hz. This also we will see shortly. And the outputs weights are Xz times Hz. Okay. So in the upside down, time is replaced by Z, the complex sinusoid or exponential in general, and impulse response is replaced by what? This was impulse response. This will be replaced by TF, transfer function. Okay. Some people also call it, or some books also call it, frequency transform. Something related to frequency. I just forgot now. Time. So this is the frequency response. Yeah. So how this is impulse response. This is frequency response. But for now, we will just call it transfer function. And what do we have here now? In the upside down, instead of this, you have simple multiplication. But notice, I haven't still proven this thing, right? Especially the bit where I do hand waving and say that Hz will represent the eigenvalues, but I never proved it. Yeah. So let's see. Firstly, of course, we should know the relation between xn and xz. As I've already mentioned, that's where the definition comes in. What is that? Xz is summation xn z minus n, right? With what is the requirement on z? Z should be in some radius of region of convergence, right? So you will have to also define what is that region. We will see some examples. Sometimes we will say it's a unit circle. Sometimes we will say it's all values of z. We'll see an example where the series that we were looking at converges for all value of z. Okay, then the region of convergence is all complex domain, right? Complex plane. So this is the jump from xn to xz. How does this transformation occur? Through the z transform. See, you give me xn, I give you xz, right? Given that z is in the region of convergence. Yeah. Okay. Now same thing happens here. For hn, what is hz? Now since this is a general formulation of z transform, you can always simply say whatever you had in time, I will multiply that with z minus n, right? And I will get the z transform, right? So that is hz. What about yz? How are these two related? Same thing, they should be, yeah. So yz is then summation yn z minus n, and each of these may have their own region of convergence. Okay. What's left to prove basically is that the convolution is replaced by product, which will also prove that hz has to be the eigenvalue, because that's what happens in product. Weights are multiplied by eigenvalues. So let's see. Do you want to take a stab at it? Want to try it? To prove that this thing in the upside down, in the transform domain, becomes this. Without, of course, you're not going to say that this is the result. You have to prove it using what you know. You only know for so far time domain, right? So let's say you know time domain and you know these definitions of z transform. This is how we define it. Can you try? Start with this and get here using the z transform. what will be the strategy?
Convolutions formula, then substituting h equals to substituting
What you have to prove is that whenever yn is xn convolved with hn, then yz will always be
that.
the z transforms multiply.
Yeah.
If two functions are convoluted in time,
Mm.
it is same as multiplying them in frequency or z trans. That's what you have to prove. So anybody knows where you will start?
Convolution.
Yeah, okay, you have the convolution, right?
Yeah.
So what's the next step?
We already found what yn equals to, and it's hc into cn.
Right, so you are taking the z transform of yn,
Yeah.
right? So that will be your strategy to get here. You will say, okay, I know that I don't know this yet.
Mm.
Yeah, but what I do know is that yz is the z transform of yn, right? So what is the z transform definition? Without using this, you know the definition is what? Yn z minus n. If you have started this, then you're on the right track. You already got the idea, okay?
Mm.
Now what can you replace yn with? What is yn?
We found yn previously.
hc.
Zn.
Or xn convolved with, isn't it? This is what you have in time,
Yeah.
right? Now you need to play with this
Mm.
to reach here. Okay,
We've already found the answer to the convolution.
what's that?
hc into zn.
So that's what we're trying to prove now. We'll not use that. We're trying to prove this result now. Convolution turns into product.
Yeah.
That is what we're trying to prove. So you cannot use that here. If you use it, then of course you've already jumped to the result. So all we have found is the z transform, right? And we also found that if zn goes in, zn comes out.
Yeah.
That's what we have found, but we haven't proven this thing yet. So now let's look at this. How do you get now 2 of this? What is xz? If you write this out, isn't it like saying xz is what? xn z minus n, right?
Yeah.
And then let's say hz is some summation hk z minus k, the whole thing multiplied. This is what's happening, right? So what you can do, like before, you can expand this as a summation, right? So let's do that. Firstly, take this away. From the last equation there, I can write equals summation. If I just use what I have done here, same thing, so it will be x k h n minus k, and this will be over k, and this is over n. You agree to that? This thing I have replaced by definition of convolution. So what remains is z minus n, right? I have just expanded this part. I haven't touched z minus n or summation over n. Okay. Remember, in the z transform, the summation is over n. Okay. In convolution, the summation is over k. Okay. Now I do a trick, which is this. I say that I can write, let's say, xk z minus k times summation n. This is k minus infinity to infinity h n minus k z minus n minus k. Can you see what happened? We replaced z minus n with what? Z minus n minus k minus k. First we start with that. It's a trick. आप करते हैं ना ऐसा ट्रिक, कंप्लीटिंग द स्क्वायर्स में करते हैं, टर्म डालते हैं प्लस और उसका फिर माइनस भी डाल देते हैं. अब अगर आप दोनों काट के if you make them zero, nothing happens, right? It's a trick to make the problem more manageable, right? Then you get a perfect square or something. So इसको अगर ओपन करें क्या बनता है? Z minus n. Otherwise, we will not be allowed to change. Mathematics doesn't allow you to touch one thing, right, without proving it. Yeah. So z minus n minus k is actually z minus n. You can just read it and see. Right? Why is that needed? Just like in completing squares, this extra term is going to help us. How? First, we notice, okay, z minus k and now xk, both of them have no n. So they can be lumped together here. Second, then you notice that z minus n minus k and hn minus k, this thing here, this is basically the same formula as in Z transform. I could easily call this thing, let's say, another variable L. Then this will be HL Z minus L, and since n is minus infinity to infinity, so will L be, right? So, well, isn't this Z transform?
Yeah.
By a different look, but it is basically just the same. So, what is this? Z transform of x, isn't it? So it's xz. What is this? Z transform of h. So it is hz. We have just proven that. Remember the left hand side was this, yeah? That yz is xz times hz, right? So what have you proven just now? You have proven that if you take the Z transform of a convolution, it turns into a product, right? And because it turns into a product like this of weights with what? Okay, it's hz, so hz must be the eigenvalues. Let's just wrap up with maybe one or two brief things. Let me first summarize very quickly the key results that we proved today. What were the key results we proved? We proved that Zn, complex sinusoids, complex exponentials, are the eigenfunctions of LTI, right? So we showed that, we proved it. If Zn goes in, what comes out is Hz times Zn, okay, provided that this Hz exists, yeah? So we talked about region of convergence for this to exist. We also looked at the definition of the Z transform, which is basically xz is summation over all n xn z minus n, right? Lastly, we showed that for an LTI system, the convolution is replaced by product, simple product in the frequency domain. Right? That's where the whole idea of, if you remember, I've been mentioning this, a huge matrix product which would be like convolution is replaced by a simple product, right? So that's what we are talking about here also. So these are the few key results that we discussed. I have mentioned inverse Z transform, but I didn't write it formally. So I'll just write that and then we close for today. We come back to more detailed definitions and region of convergence next time. Inshallah. For now, I just want to write, because I have written now, this is the formula for Fourier Z transform. Is it complete like this, or what's missing? What do you have to mention with it? They have to go together. I have to mention region of convergence, that Z, whatever Z you want to use here, has to be within the region of convergence. Okay, we'll see this in more detail next time with solid examples. Then you will know what I'm talking about. You already got the idea, but we will make it more solid next time. Z transform, convolution becomes product. Another term, right? Convolution becomes product. Zn goes in, Zn comes out. That's one result. Here. Last thing I want to write is the inverse Z transform. We sometimes write it as this big Z times operating on YZ. Okay, and for discrete, for this kind of, for the Z transform, it has a bit involved definition. YZ Zn minus 1 dz. Okay, it's a contour integral. Okay, contour integrals, yaad hai? Don't worry, we won't go into much of this detail. Just try to read up if you need. We will not use this formula in this course at all. Okay, there is another shorter method called partial fraction expansion that helps us get Z transform, inverse Z transforms. Okay, we will come to that probably in the next lecture. But for the sake of completion, I'm going to mention, just like you can get Z transform by this formula, writing it as a projection, you can do this thing where you write Yn as a linear combination of Zn's. Remember? What are these then? The weights. Where is the linear combination? Integral. Okay. Contour thing comes from the problem of working in the complex, discrete complex problem. Okay. So we will see that later. But and this also is, when you try to prove it, you will see. Maybe it's in the book, I think it is. But we don't need to dwell on it too much. What you need to notice, an important difference. When we were going from time domain to frequency, we use summation. When we are going from frequency domain to time, we are using integral. Why is that? Any thoughts?
Because in time domain we're dealing with discrete. In frequency domain we're dealing with continuous distance.
So essentially, it's very important distinction. The discrete time signal, of course, is discrete time. You have already defined it that way. When you are going to take its Z transform, you are working with something that is discrete. Yeah? And then you're going to write it as transform. The transform itself is actually, in general, it is continuous. Okay? And then if you're going to go back to discrete time, or to the signal, you need to work with something that is continuous. So you have to work with integrals. Okay? Just let that sink in. Think about it a while. It's like saying this, that if I'm going to write something as a sum of sinusoids and or maybe this can take longer. I'll draw it next time. Yeah. For now, just keep this in mind. As your colleague said, basically the difference is from here. Xn was discrete, whereas even within this formula, okay, only this is discrete. The whole thing is actually continuous. Xz is continuous, and that's why when you work with xz or yz, you have to take integrals. Okay, xz can turn out to be discrete. There is a special circumstance when it can happen, but in general it will be continuous. Right, so any questions? Any questions? आप में कोई SNL तो नहीं देखता? Saturday Night Live.
Yes, कभी कभी
अच्छा, वो टॉम हैंक्स का उसमें होता है. Just Google it, Tom Hanks Halloween skit on SNL. It's very, उसमें वो कहता है हमेशा. Any questions? Yeah, just check it out. You'll like it, especially if you're an SNL or fan of sketches. Yeah. Okay. कोई है या नहीं वैसे? अच्छा. ठीक है, चलें, सही है. Thank you so much.